Hello, everybody. We welcome you today at tinyML Meetup Talk. This event is the first event in a tinyML Meetup group that we launched in Grenoble, France, to support the French ultra-low power machine learning community and to expand the tinyML ecosystem. My name is Irina Sizova. I'll be a moderator of today's tinyML Meetup discussion. We initially planned to launch this discussion in French, but we are very happy to welcome today 80% of English-speaking attendees. And at the last moment, we decided to keep the discussion in English, but you may ask your questions in French and we will respond in French. After this discussion, we'll launch a quick poll to ask what tinyML subjects you are interested in and the language you prefer, which will help us to plan the right format of the event in September. We are starting the talk in several minutes. While the speaker is preparing to give a talk, I have to mention a couple of words about the sponsors who contributed financially to this project and made it possible. And the tinyML Vision Challenge, which is going to be taking place in August 15th. Please have a look at tinyML website to find more information. We have also the next tinyML talk that's going to be in July 6th. You can all join online. Please find out more information on tinyML website as well. So today I'm presenting the speakers. Frédéric Pétrot holds a doctorate in computer science from Pierre et Marie University. His work focuses on the design and implementation of integrated digital systems for general specialized purposes, for example, for the acceleration of artificial intelligence. We have Etienne Balit, who obtained a master's degree in modeling for cognitive science at École Normale Supérieure. At Neovision, he coordinates the R&D team and monitors the latest scientific and technological advances. And we have Loic Lietar, who just joined us from a plane, who just came from Barcelona. He's a co-founder and the CEO of GreenWaves Technologies, a fabulous semiconductor company that designs the disruptive ultra-low power embedded solutions for highly power-constrained devices, such as hearables, wearables, and IoT sensors. He has been an active business angel for the last 8 years. Frédéric, at this moment, I'm giving you word. Please share your screen.
So, hello everybody. Today I will quickly go through some thought about ultra low power neural networks and more from a technological standpoint than an application standpoint that my esteemed colleague will talk about after. And first of all, the first question we have is what kind of AI do we really need? So I prepared some jokes in French, so I won't do them in English about that, but you can have the eagle eye or something that is less efficient than that, but that still has its place in nature. And another example is this one. You can have Albert or Homer, as you wish, but even though Homer may not be so well equipped, he's still able to do quite a lot of very interesting things with his brain. So it's why it's important to try to see what we can do with limited resources. This chart is quite interesting, I think, because it gives a plot on what are the current neural network architectures in terms of number of parameters. This is the size of the bullet, number of giga operation you need to perform here, and the top one accuracy on the ImageNet classification. And so at the end of the day, what we would really like to have is something that fits here and is very small, because it's where the power efficiency and accuracy is better. And what we can see is that there are quite a few neural networks that go toward that direction, but they are still quite big. And the question is, what can we do from a technological standpoint to try to help this neural network in terms of implementation? So the first thing that we can do is to do hardware acceleration for neural networks. Currently, most inference engines are running on software, either on a GPU or CPUs. But it's no surprise to anyone that is doing digital design that software is not so power efficient than we could expect. And so there are some reconfigurable hardware, which is called the FPGA. Most of you probably have heard about that. And the colleagues at Intel have been doing some work on evaluating the performance per watt for this other technology. And they say, okay, FPGA is 1 order of magnitude better in performance per watt than can be a CPU and GPU. And what you can see also on this chart, on these measures, is that the application-specific integrated circuit, so dedicated hardware, is also 1 order of magnitude better than FPGA. So you can have a factor of 100 between something running on software and something on a dedicated ASIC in terms of performance per watt for artificial intelligence applications. So this is something that we have to have in mind when we want to do ultra low power on neural networks, for example. So what's the interest of having such a good power efficiency? Okay, if you are working on servers, I would say it may not be the most interesting thing to do, but even so, not all AI tasks require very high accuracy, very high throughput. And so you can minimize your total cost of ownership for the AI workloads. And also something that is raising in importance is the social acceptability of AI in terms of power consumption. And so if you have greener AI, it's better for you. But what is really interesting for us is really these local computation possibilities. Because when you do local computation, you will gain a lot in energy. You don't have to exercise router, cloud servers, and so on, which is a huge constraint in edge and IoT computing. You can have very small latency. You don't have to connect to a remote server, so you can have immediate response, and you do not depend upon the communication capabilities of where you are. And something that is also quite important in terms of social acceptability is privacy and security, because you do not have to store stuff in someone else's servers, and nobody can sniff what are the data that you are sending. So these local computations is something that we want to do clearly. So the constraints that we have really depend on the application, and clearly it's a matter of silicon resources, and this can be classified, in fact, in two things also: computations to perform and weight, storage, and access. So it's really where you have trade-offs to do. And as I would say, orders of magnitude, the typical constraints that we have in terms of watt for AI processes is something like 10 to 100 microwatt for wearable, 10 to 100 milliwatts for phones, 1 to 10 watt for plugged edge devices, and 100 and more watt for plugged cloud devices. So clearly, we are much more interested by this type of constraints from our side. So where can we earn in terms of power efficiency? In fact, it's a matter of what is the type of computation you are doing. These two plots here are interesting because they compare the power efficiency of floating point arithmetic, as you can see here, versus integer arithmetic. So on 16 bits, you can see that you have a huge interest in terms of power efficiency to do integer arithmetic. Here it's important to note also that the scale here is logarithmic. So each time you double, you have in fact an order of magnitude difference between the power efficiency. So this is true clearly for addition. It is a bit less true for multiplication, but still it's quite interesting to see this kind of comparison. And in terms of area, it's also quite important to do integer arithmetic. So there is also a lot of memory accesses that are performed during inference, because you need to get access to your weights and to the data on which you want to perform the computations. And here what we have is the energy that is used when you are doing memory accesses. If you are assuming you have a system on which you have a static local memory here and a dynamic memory outside, what we can see here is that the fact of accessing internally the memory is in the order of 5 picojoule, where it's in the order of 600 picojoule when you want to access the external DRAM. So clearly, you need to do your computation locally and have as few weights as possible outside, I would say. Otherwise, you have the type of energy consumption that is spotted here. So my last slide to summarize a bit these ideas is that what you need to do if you want to go for low power inference is first to simplify the operation that you want to do. You will avoid a complex operation like sigmoid, batch normalization, and this kind of stuff. You don't want to do floating point arithmetic. Do not use floats because it's not hardware friendly. The alternative here is to use small types. For example, you can think of 16 or 8-bit integers, but you can also go to much smaller types, and there is quite a lot of work on binary and ternary inference, and they show very promising results. There are also architectures in terms of system re-architecturing, in which you want to have a lot of memory cuts on which you can do the processing, because you will be able to access your data quite wisely. Or you can even, it's more disruptive, but integrate computation into the memory itself. Regarding the frameworks, if you want to work with very low low number of bits types, already today we have some solution in the traditional framework like TensorFlow or PyTorch, and you can learn already with small weights and activations. And people at Xilinx have been done because they are selling FPGA, so they are promoting, I would say, the use of small data types, because they have a lot of inherent parallelism in their circuit. And so what they have done as a trial is to relearn on some network with less bits. And what they show is that if you increase slightly the size of your network, but if you drastically lower the number of bits of your weights and activation, you can have very high gains in terms of power efficiency. So that's it for me. Thank you very much for listening.
Frédéric, we already have a question for you. How does all this map to specific processors?
Okay. I would say currently we don't have, I would say, vectorized operation working on a low number of bits. So regarding the data types, it's something that, okay, we have to think of. How do we do this kind of operation at low cost on software? Regarding inference at large, if you are working on bytes, for example, you can use multi-core platforms that are dedicated to low power applications. So this is one solution, because this platform usually are based around a network on chip and a lot of memory cuts. And so you can access your memory the way you would like and be quite power efficient.
Okay. Any comments regarding reconfigurability per application need?
Yes, sure. When you are targeting FPGA, I would say I would not say this is easy, but this is a matter of designing the right hardware that you can reconfigure on your FPGA. If you are targeting something that is more software oriented, then you need dedicated tools, I would say, in front of your system in order to partition your network and do all the stuff that allows to map that on the type of multi or many core system on the which you would like to run your inference.
And another question, is there a mechanism to get this result to the processor vendors?
Okay. I would say they have these results clearly because typically NVIDIA was working on very low bit stuff at one point in time. I would say the people that have been doing these experiments are at Intel. Intel is a company that is selling processor and not really hardware accelerators. Even so, they are doing specific acceleration for with their small USB key. So the processor vendors are aware of that. Now, how can we do that in a more power efficient way towards other type of processors? I would say it's really a matter of, I mean, they know. From my point of view, they are well aware of that.
I have lots of questions for you, Frédéric.
Yes, and perhaps what we can say is I'm sorry for the people that are asking questions, but probably Loic and Etienne will also enter the game. They have things to do about this question, so I would rather
yes.
let them do that presentation if you don't mind.
Yes, Etienne, please take a screen.
Hi everyone, I'm Etienne Balit as present me, and I will focus on my part more on the use cases and introduce some questions that I hope we can discuss afterward. So I tried to look in commercial application that everyone can relate to of tinyML today, and I found some that I think will talk to everyone. So first, Alexa. I will mention what tinyML is used in Alexa, and the Echo Dot from Amazon, the Vector, a toy from Enki Robotics, and connected bracelet like Fitbit. Here it's the Xiaomi in this case. So in those three, in Alexa, it's used as a wake word detection to detect the Alexa was pronounced and to start the more costly processes of analyzing using cloud inference. In Vector, it's used for face detection, most notably, but not only. And in the case of smart watches, and it's used for activity recognition using accelerometer data and such. So it seems like it's used a lot in toys and gadgets. I'm being a bit provocative in saying that, but my following slide will explain a bit why it's an interesting thing, because I'm wondering if tinyML is a disruptive technology in the sense of starting with low quality use or scenario where we can afford low performances, but the question is, can we go, and in what time frame might it reach parity with the inference that we currently need, the cloud inference or accelerator, like high-end accelerator, like will we reach parity or not, and in which time frame, or will it always be in some kind of niche use cases that can afford those lower performances with slower accelerators. So the other question that I think I can mention a bit about, and then I think we'll also talk about and discuss afterward, is how do we know if use case is doable on device? And we would all love to have a clear-cut answer for different use cases, but in fact there is 3 zones that I think of. There's the possible use cases as of now, the one that are impossible, but there is a way bigger zone that I would call the trade-off zone. And here in this zone, the experimentation is the only way to know if the performance that can be reached are compatible with the business requirements. And can we afford the trade-offs that are necessary to make it light enough to be embedded on device? So to give some example and then start with the I would say negative side of the equation. The example of use cases that I think are impossible or at least will be in the near future impossible on device. So the first one is real-time translation from English to French, for example, translating it in French for people that would need it in real time. Full language understanding. So, for example, for Alexa, processing everything on the device with low cost and low consumption chips, and not using stronger and faster accelerators. The pedestrian detection and tracking. So tasking and overall task in ADAS or in other domains where we have a real need for high precision, and we cannot afford any misdetection. And most of medical diagnosis tasks. So for those use cases, and of course many others, we will for the near future will need to rely on edge on premises or on cloud deployments. So now for the more positive side. So of course, the one that I mentioned earlier, so activity recognition, face detection, or wake word, but also all kind of presence detection. So for detecting that the person is in a room, but it could also be other kind of things. There was an application, for example, for detecting that the shelf is full or empty. So that kind of use cases, I think, are definitely possible as of today. And now the biggest zone for me, that I think, is the one where there is clear trade-off, and it's doable, but we'll need to cut some things. So, for example, people detection and tracking is possible in some scenario but there is trade-off on the position of the camera, on type of sensors that you will use, maybe use other modalities. So there definitely is possibilities, but it's not something that can be said right off the bat. It definitely need experimentation. Face recognition, also the same idea. there is trade-off in terms of performance and how much false positive, false negative are acceptable in this domain. And for example, there is definitely face recognition on some, for example, the vector that is using face recognition but as a toy. If the recognition fail, it's not that much a big deal in a sense. Also, object recognition, so probably trade-off in terms of the number of different item of different type of objects, but also maybe the time that will need to be taken, and probably the complexity of the classes that need to be differentiated. The same thing with defect and damage detection. There's definitely some use cases that could be done with tinyML solutions, but not all of them will be doable, and this is where experimentation is needed. And the same for optical character recognition. In the case of case tracking, it's more a matter of precision in the tracking and number of frames per second that can be that are needed. And but there is a lot of progress on this. So yeah, so the question for me on this is do you agree with those use cases and this division, and which are the one that might be in the future go from a clearly in being a trade-off kind of use case to the clearly possible and non-problematic to reach. And to end with a bit of questioning on why we are doing this, I wanted to ask a question on why are we really doing trying to do computation on device, but at the same time we have a proliferation of smart light bulbs that need an internet connection. So I think it's good to think against ourselves and really ask: is the use cases from the market already here, or is it still an ongoing process? Thank you.
Loic, at this moment, I guess it's please start your presentation, and then we get back to the questions that I have.
Etienne has to release the screen.
Yes.
Yeah.
Okay, thanks. Oops, sorry, I need to go back to the beginning. Okay, good evening. So I'll give you the point of view of a processor vendor. This is what we make. So we are really in between Frédéric and Etienne to make it a bit simplistic. A typical tinyML system is very classic IoT stuff. You have sensors, you have a processor, and you have communication. Now, the sensors, and it was well shown by my colleagues, we always think about cameras and microphones, but there are many more that are very interesting, and I mentioned a few here. Infrared sensors are great from a privacy perspective, and they are getting pretty low power now. Radar is fascinating. It's fascinating because the human cannot interpret a radar signature. You really need machine learning to interpret that. And the last one is bone conduction microphone, which in practice are 3D accelerometers. And out of that, you have a number of use cases that expand. On the processor side, I understand the hype around AI. We shall not forget that the traditional DSP is not needed anymore. We need it, and therefore we need processor architecture that can do both very well, AI and DSP, because in tinyML, you have only one processor in the system. You don't have the luxury of having multiples. The last comment on this slide is just to give you an idea of the power budget on real cases. If you take a smart camera that is battery powered with a AA battery, you want 5 years of autonomy. This gives you 300 microwatt on average for 5 years. Okay. Now on the other extreme, if you take an earbud, it has a coin cell battery and 12 hours of autonomy, which is becoming the state of the art, gives you 15 milliwatts during that period on average. So this is the type of budget we are working on. So those are real life examples, again, on a battery. Voice command, smart cameras were discussed before, but others that are maybe less well known by you guys. So smart door lock, which is very popular in Asia and in Japan, with Face ID increasingly from fingerprint to Face ID. Counting people in meeting rooms here with an infrared camera that you attach on the ceiling with the processor. Gesture command with radar signature. This was pioneered by Google, and I think this will pervade wearable devices. And then even more sophisticated cases, so voice separation aided by lip reading, which helps remove the noise around the person that you are listening to. Automatic noise cancelling aided by acoustic environment classification. So ANC works well depending on the environment you are in. And if you know that environment, then the model is better. You can tune it. And finally, and this is my favorite, it's voice separation aided by locutor voice ID. So if I'm talking to you on the phone in a noisy coffee shop, my earbuds are aware of my voice and they're able to remove everything but my voice. So you will only hear myself and not the noise. So you see there are fairly rich cases that today can be run on a battery on something that is, let's say, a big microcontroller. Now here, this is something trivial, but let's not forget about it. A problem is better solved when you archive. So in this example of Face ID, if you start by recognizing that there is a face in the picture, this is a low complexity algorithm, and therefore it consumes little energy. And then you go to Face ID once you have found the face. And typically here, you gain a factor of 10, which means that you can use a simpler algorithm, and therefore you have a simpler, less costly system. Another angle, of course, is to use multiple data types together to facilitate the classification. And here in that ID case, if you use Face ID, so image plus voice, you would make a system much more robust or much simpler and consume less. And of course, there is nothing new, but let's, as we discover and explore AI, let's not forget about those basic principles. Now, when you look at designing a tinyML, what are the system dimensions? Of course, accuracy, and this was mentioned before. And from a real-life perspective, there is still little specific knowledge on what is acceptable. Is 80% or 85% or 90% false positive, false negative acceptable? You see on one hand that academic, killed for 5 point more. We don't know, frankly, and our customers are struggling as they consider to deploy real system to decide what is the right accuracy they should target. Autonomy is another one. And here, the order of magnitude matters. It is 1 hour, 10 hours, 1 day, and so forth. And what we have learned is no one will be changing a solution for 20% more autonomy. It's really, you need to set up the class, and that's it. And then, of course, you're down to cost. So unit cost is definitely dominated by the size of the AI model you are using. And I have designed those red arrows that shows that everything is connected to make the system decision difficult. But this is going back to Frédéric's initial slide on complexity versus accuracy. There is a lot of things at stake from a tinyML perspective because, of course, you have very little memory. And finally, development cost, and the cost structure is very different from what companies are used to. The training data set production, so having your own data for your own use case, can be extremely expensive. The model training cost can be very expensive, even if it's only incremental. Today, training a model from scratch is inaccessible to most companies. Only the very big companies can afford that. But even if you want to adjust and modify this model, it's very costly. And finally, the model complexity reduction, which is something, again, that Frédéric alluded to, where you start from a well-known model and you simplify it, you quantize it so that you can fit your objective in terms of accuracy and cost, as well on the architecture porting. This can be very costly, especially because it's a lot of trial and error process. And the problem is that none of all this is really mastered today. We are really at the beginning of the story. AI advances are still largely made with little consideration for hardware. So those guys assume that they have infinite hardware resources. Open source models and data, which has been the case from the beginning of AI, is losing momentum as we move from academic to commercial applications. And people have become very privy of their secret sauce, and this doesn't help. The complexity reduction methods are still very empirical, and the tools that we use to support that are not much performing nor predictable at this stage. Okay, so you start a project, but you have difficulty in understanding where you will land and when. The AI state of the art is moving very fast and faster than silicon can. So it takes at least 2 to 3 years to have a new processor. But in the meantime, the models, the best-in-class models will have evolved. So the processor architecture shall therefore have limited specialization to remain very programmable, to avoid immediate obsolescence. But at the same time, if you are fully programmable, as Frédéric said, then you are not very efficient from an energy perspective. So you have to be just enough for the architecture to be efficient as you want it. Okay. On the data, beyond the classic images that everybody is using to do benchmark, the voices in the mainstream languages, the training data production, or even the enrichment has to be done, and it's little productive. And if you go the path of data fusion that I alluded to for face and voice, for example, image and voice, for example, those things get even worse. Okay. And last, applications are very fragmented, which means that as long as we don't have generic methodology, I'm afraid that each time you have a new system, you have to go through all that once more, and there are limited synergies from case to case. Now, the good news is the research has never been so active on all fronts. If only on the processor architecture front, we have not seen that in the last 30 years. So this is great news. But it's really work in progress. So as a conclusion, tinyML is really opening the door of AI to an endless number of microcontroller applications. So very small footprint, battery operated. This is interesting. I mean, we are selling billions of microcontrollers in the world every year. But the toolbox is still in infancy, and we have to deal with it. And therefore, the adoption threshold remains fairly high. And we are all committed as an industry to lower that threshold. And I'm really convinced that this will be one of the most innovative markets for the years to come in that space. Thank you.
So we have still lots of questions. Let me read them. Can we run object detection networks on the microcontroller?
Again, this one is for Loic.
I'm not familiar. We do. Yes, we have. We use typically MobileNet V1, V2, V3. Some I think YOLO is more complex. I'm probably not. Maybe Etienne can. We have some benchmark, but for sure you cannot do a 10 frames per second, right? But in tinyML, you don't. Usually because you are on the battery life, you are monitoring things that don't change very rapidly. So you are happy. If I take the example of people counting, you would make one count every minute. You don't need to make one count every second. And as such, if you need some accuracy, you can run fairly large networks, provided you have the energy budget. And it will take you a few seconds in real life. So yes.
Yeah, so we can definitely do run object detection architecture, but they are adapted to tinyML settings, as Loic mentioned. So Yeah, notably the MobileNet family is good for this this type of adaptation and making it small enough to be able to put it on embedded systems.
Etienne, I think the next one is to you again. I'm curious why this is positioned as a choice, embedded versus cloud. Is any connected application, isn't a distributed approach possible? Combining the benefits.
Definitely possible. It's the example of Alexa, I think, is really interesting for this because they use embedded algorithms for the wake word that is running all the time, as it need to react fast to being called. But then everything else is done in the cloud. And there could be more complex architectures with gateways, local gateways that use faster accelerator and that are not on battery. Definitely a lot of architectural choices that would be possible. Yeah, and I didn't to say at all that it's a choice that has to be made. It can be a mix of both.
Yes, if I may add to that, what we see is that you can see each sensor with the local AI that produces metadata, and they are uploaded, and you have thousands or tens of thousands of sensors, and on which AI models will be applied to in the cloud. This is really current architecture.
But sending data through the air is something that is not free in terms of milliwatts. So it's always a trade-off from that perspective.
Yeah, but if you start from, say, a 1 megapixel image, and the resulting number is there are 3 people in the room, you have compressed dramatically the amount of data.
Great.
How do you deal with all internal connections inside the FPGA that is challenging when implementing CNN?
Okay, so this is a quite technical question. So it's really a matter of finding the right architecture on the right FPGA. So, okay, I guess the question is a bit harsh to answer because it's really related to the hardware implementation that you choose and the microarchitecture that you want to have on your on your hardware. Somehow you have the choice regarding the parallelism that you want to have. If you want to have very high throughput, you will have something that is very parallelized, and then you will have a lot of fan outs on your wires. If you can live with serializing part of the computation, then you can have it can be implemented in a reasonable way, I would say.
Thank you. Don't you think that lack of people having both AI plus embedded systems knowledge is one of the problems in today's progression of tinyML?
Maybe I can answer shortly part of the answer at least. I think that definitely there is a bit of that, and especially the software domains, I would say, in between the machine learning part and the embedded development are really different. They work differently. For example, the machine learning is really open, and you can often have a lot of code that you could use to infer how things are working. It's from what I saw in coming from machine learning and going in embedded development projects is that it's way more closed overall. So this I think is also a problem more than the lack of people that are already have those two skill sets. Is that it's hard for someone from machine learning to acquire a skill set in embedded system, and I think the the opposite is probably the same problematic.
Okay, the challenge more than people is immature methodologies, flows, and tools. If probably we saw the same thing, I don't remember if it was 20 years ago or 25 years ago with DSPs, right? I think today DSPs is fairly standard. There are good compilers, there are libraries, everything is ready, and you don't need to be understand the guts of the machine to program that. We are not there yet on the AI, for sure.
As a teacher, I would say currently at least it's not so easy because people that are specializing in embedded system are really the ones that do not love math so much, whereas the people that are specializing in AI and data analysis and so on are loving maths but do not like bits. So it's some kind of a stretch, I would say, from that point of view.
So we are in the era of artists, and but the tools will get out of that.
Yeah, sure.
This is an interesting one.
I think I have a question that relates to this. Is I feel that most of the development of tool sets are done to help people that comes from embedded development to do tasks in AI and to integrate AI. And I'm wondering if there is. It seems that there is a lack of tools that are made for people that know machine learning well and that could go and implement particular like missing components of frameworks. And that's also what I mean by closed ecosystem, is that you cannot really look into the system and just adapt it. And this is what I'm wondering if it's because the target of most toolsets are in fact embedded developers and not machine learning practitioners.
I think it's because it's a difficult problem and we have not solved it as an industry.
Do you think RISC-V would help with speeding up the silicon design to catch up with AI modeling?
I can take this one because we are a RISC-V based company. RISC-V is giving us the opportunity to innovate at the processor architecture level, which you could not do with ARM. So yes, so it opens up. And at the same time, my frustration is I think there are very few companies that are innovating with RISC-V. They are enjoying the low-cost side of it and not the opportunity to innovate. But yes, definitely. And I mentioned to Frédéric on the side, we do have vector extension that are 2, 4, 8 bits for vectorization. And we could not do that with ARM. We can do it with RISC-V, for example.
Thank you, Loic. I'm new to the field, but what makes tinyML different from a microcontroller board?
I'll take that one. A microcontroller can run neural network models. It will not be very efficient from an energy perspective. So the innovation, the architectural experiment that microcontroller companies are doing are to make this much more efficient, and typically with some reasonable architecture extension, you can improve the efficiency by 1 to 2 orders of magnitudes. Okay, so the traditional one you will not go very far, but a new generation of microcontroller is coming out. But again, we are at the beginning.
I'll probably announce the last question because we are running out of time. And while I'll show the slides on the sponsors, you can respond. Coming back on distributed AI topic, but more than simple wake-up mechanism, are there any advanced research on that taking into account energy budget for communication?
It's very difficult. We have tried to model that and to understand, whether it's worth doing a task on the edge side, on the cloud, or you might have 2 steps, by the way, the very edge, the edge and the cloud. and it's not that scientific. So basically today, or at least the approach we have seen working is you start from the autonomy, the budget that you need, that you can afford on the very edge, on a battery, and you do everything that you can, and the rest you upload. Okay, for sure, whatever you can do on the very edge from an energy standpoint is better to do it there than to upload it. But again, it's a lot. We are still in a trial and error approach, and I don't think there are robust methodologies to tackle that.
Thank you very much. We're having. Let me check if I will choose another the last one. The last one question. I still have a couple minutes. I would take the view of whether the instruments gathering data in front of the analysis could use tinyML processors better than the processes they have in terms of speed and cost explicitity.
Not sure I understood. Frédéric or Etienne, have you understood the question?
Okay, I'm not sure I fully understand the question, but if I understand well, the question is, can we do some lightweight pre-processing or something like that? Yes. The instrument gathering data is something, the on-device pre-processing that we would like to do, and perhaps do what the kind of thing that you were talking about, Loic.
Yeah, there are a number of cases in which we would do some classic digital signal processing. Let's call it normalization of the data, for a better word. That would then facilitate the work of the neural network that is applied to the data. If that was the question, yes. Hence the interest to have processors that do well both.
Well, our time is unfortunately over. Thank you very much for all the speakers. Again, I'm sorry we didn't answer all the questions, but we will email all the responses and they will be posted on the tinyML forum. Thank you again for coming to this talk, and we are planning we're targeting a second event in September. So stay tuned. Thank you so much to everybody and have a great day.
Thank you very much.
Thank you.
Bye.
Have a great day. Bye.